Okay, so I'm now going to try and solve what was the most difficult question, or the question that was answered the worst, which was this question 13 here. Statement, it can be shown that the period of a body oscillating up and down on a spring, t, that's the period t, is a function of its mass m and the spring constant k. Write that statement in a mathematical way. Let's do that first. Well, it's fairly simple, and it goes like this. The t, the period, is a function of the mass and the spring constant. That's all you have to write. The second part of the question, so that's part A. The second part of the question asks you to use dimensional analysis to determine a possible equation for the period t of a body oscillating on a spring. So we've done this in class 18 times. So t is c m to the x k to the y. Okay, well, we know the dimensions of m are kilograms, but we need to determine the dimensions of k. Well, we can determine the dimensions of k by using f equals kx, which you've done with Miss Ruth, which means that k is equal to f over x. Okay, so k is going to have the units of newtons per meter. Now, how can we get the dimensions of newtons? Well, we could use the equation f equals ma. So we're going to write here using f equals ma, the newtons, dimensions, this is dimensionally, you can't really put equals, is kilogram, meters, seconds to the minus 2. And those are the units of acceleration, and that's the units of mass. Putting it back up here, so k for units must be kilogram, meters, seconds to the minus 2, meters to the minus 1. The meters disappear, and you get kilograms, seconds to the minus 2. So we're going to put that back up here. We're going to put them both into the equation. So that equals c kilograms to the x, and then kilogram seconds to the minus 2 to the y. Okay, well, we don't need the c because it's dimensionless. So we can write dimensionally, okay, t is equal to kilogram to the x, kilogram to the y, seconds to the minus 2y. Okay, so on the left hand side we have seconds, which gives us seconds to the 1, kilograms to the 0, meters to the 0. On the right hand side we have seconds to the minus 2y, meters to the 0, and kilograms to the x plus y. And now we just equate them. Okay, so we're going to equate these together, and as we equate them together, it's going to be seconds are going to give us 1 is minus 2y, which gives us y is minus 1/2. Kilograms, we're going to get 0 is x plus y, and so if you put the y into there, x must equal 1/2. Just think about it for a couple of seconds. And then meters, we're going to get 0 equals 0, which we knew anyway because we're not stupid. So we have x as 1/2, y is minus 1/2. We put it back into the equation right at the top here. Okay, so we're going to put it back into that equation, and we're going to get t is equal to c m to the 1/2 y to the minus 1/2, which is c m to the 1/2 over y to the 1/2, which is c square root of m over k. I don't know why I called that y. That should have been k all the way along. Okay,